Yeah, now PPT is visible. Module 1, simple and compound stresses.
No, sir.
No? Okay, 1 minute.
No,
Now PPT is visible.
sir.
Slide number 1,
Yes,
module 1, simple and compound stresses. Right?
yes, sir.
Yes. Yeah. Now shall I start?
Yes, sir.
Yes. Okay. Yeah, now we start. Already we started our syllabus. Yes, please mute yourself. If you have any questions, then unmute yourself, then ask me the question. Okay? Yes. So in module 1, actually is a linear elastic, right? And second topic, simple and compound stresses. Directly I will take the second topic here. Later I will come to that first topic. Now in the second topic, in the module 1, simple and compound stresses. First we study the simple stresses. First we should know about what do you mean by stress, then strain. Now PPT is visible. Yes, give me some response.
Module 1, simple and compound stresses.
Yeah,
That,
that PPT is visible, right?
yes, sir.
Yeah. Now in that module, first we should know what do you mean by stress. Stress is nothing but an internal resistance force offered against a cross-sectional area of a member. Then that member is subject to what we call as a stress. How already we studied how physically we represent, how physically we define a stress, and mathematically stress we represent as load by cross-sectional area. The unit of stress is Newton per millimeter square. Then types of stresses based on the type of load acting on the component, we categorize the stress as one is tensile stress, second one is compressive stress, third one is shear stress. Right? In tensile stress, what type of load is acting here? Two equal and opposite forces acting away from each other. Acting where? Along the central axis of the member. Then the member is subject to what type of load? Tensile force. The tensile force over a cross-sectional area, is called as tensile stress. Similarly, compressive stress, two forces acting towards each other. Then shear stress means the force are acting on the surface area, right? And the other types of stress also we discussed. One is a bending stress, another one is a twisting stress, and third one is a bearing stress. One component plays over the another one, you get bearing stress. After that we discussed about strain. Strain is, before going to define a strain, first we should know the deformation. Deformation means when a load occurred on a component, the change in dimension takes place on the component, on a body. When it is subjected to an external load, that body undergoes what? Deformation. Strain is nothing but the change in dimension to the original dimension called as strain. Right? Then different types of strains are there based on how the body is changes its dimension. It changes along the axial direction is called as longitudinal strain or axial strain. It changes in dimension along the lateral dimension, then it called as a lateral strain. The change in shape of a body when subject to an external load, shear load, then is called as a shear strain. Right? Then we discussed about stress strain diagram for a mild steel or is a low carbon steel. Right? And all the salient points also you can see that one is proportional limit, elastic limit, right? Then yield point, that is upper yield point, lower yield point, ultimate point, and fracture point. These are the 6 salient points in the stress strain diagram. And also you see the stress strain diagram for other materials also. Then in the stress strain diagram, we can see that up to elastic limit, we have a relation stress is directly proportional to strain within the elastic limit. That is governed by the scientist Hooks, that's called as the Hooks law. Hooks law states that within the elastic limit, stress is directly proportional to strain, right? Then in order to remove the proportionality, we get a constant. That constant is called as proportionality constant, or is a modulus of elastic, or Young's modulus. The Young's modulus is defined as it is a ratio of stress by strain. Then also we discussed what are the mechanical properties of materials. First, properties of materials are it may be a chemical property, physical property, mechanical property, and dimensional properties. So many other properties are there. In that we discuss mainly a mechanical property of material. Mechanical property means when a material is subject to an external load, how the material behaves when it is subject to an external load. That tells the mechanical properties of material such as strength, stiffness, ductility, malleability, elasticity, plasticity, resilience, toughness, brittleness, right, fatigue, creep, etc. Right, and one more is important property is hardness. Then we discussed mechanical members. Mechanical members are nothing but in an machineries or in an aircraft, all are called as structures. Structures are nothing but is a load carrying members. In the load carrying member, the members are subject to only an axial load. We categorize those members are called as bars. Now this is the best example I take is a bar is a circular cross section. It is subject to what type of load? Only axial loads. It's called as a bar, right? And then if the member is subjected to a load, it may be axial, inclined, or any movement, then that member is called as a trusses, right? Then if a member is subject to only a transverse load and an external movement, then it's called as a beams. Or if a member is subjected to only a twisting movement, consider this is a circular but subject to only a twisting movement, means for transmit the mechanical power from one end to the another end, then the member is subject to the cylindrical member are subject to twisting or torque called as shafts. Then one more is if a member is subject to only a compressive load, it failures to only a buckle, right, lateral deflection, then it's called as a columns. These are the few members, mechanical members we discussed in last class, and also we discussed the syllabus. Now today we are going to start the syllabus in that module 1. Already these contents already we discussed, right? Before going to study that, first we should know what are the assumptions. Before going to derive any equations, before going to study in theoretically for a component, these are the assumptions you must know. These are common assumptions for an in an engineering materials or engineering design of the components. What is the first assumption? The first assumption is the material obeys Hooke's law. Now
Sir,
the
we
slide,
can't see that PPT, sir.
this slide is not visible. Assumption slide.
No, sir.
Okay, 1 minute. Now it is visible.
Yes, sir, but it is. Yes, sir. Yes, sir.
Assumption.
The slide number 2, assumptions. Okay. Shall I start?
Yes, sir.
Yes, sir.
Yeah, the assumptions. Now, so before going to derive any equations, before going to derive the deformation or stresses induced in a member, these are the assumptions should know that. Okay, so what is the first assumption here? The first assumption is material obeys Hooke's law. Now, what is the Hooke's law states that within the elastic limit, stress is directly proportional to strain. Right? Only whatever the load we are applying here, that load should be within the elastic limit only. There is a first very important assumption. It will not crosses the yield point, or it will not undergoes, the material will not undergoes any plastic deformation. Right? There is a first assumption, the material obeys Hooke's law. Right? Second one, the material is homogeneous and isotropy. Now what do you mean by homogeneous? Homo means same kind. Right? Genius is the kind. So homo means same. Genius is nothing but kind. It's the same kind. So material is homogeneous. For example, if you take in our body, if you take a blood sample in any part of in our body, that chemical composition is same. Is it right? The chemical composition of the blood is same. Means the blood is a homogeneous material. Similarly, whatever the material engineering materials we use for a machine element, for a mechanical structures, that chemical composition of that material remains same. Then it is said the material is homogeneous. Second one is isotropy. Again, iso means same, tropic means is property, is the same property. Means if the material, if you consider in all the direction, the mechanical property remains same. That will not changes. That will not changes with the place to place. In all the direction, the material property remains same in all the direction. Then you say the material is isotropic. These are the two. These are very important assumption. The material is homogeneous and isotropic, because we are dealing with theoretical analysis here, not the actual experimental or numerical one here. Okay, this is second important assumption. The third assumption, it is similar to the first one only. The member is loaded within the elastic limits. Means if you apply a load up to elastic limit, you can apply the load, not crosses the elastic limit. Why? Means if you remove the load, the material, the body should come back to the original shape and size. That's why whatever the load we are applying the material within the elastic limit only. Next, the fourth one, deformation within the elastic region are very small. If you apply a load here, whatever the change in dimension takes place in the member, the deformation is very small as compared to the, say, take a rubber, okay, plastic. If you apply a load, it deform more, right? But when it comes to engineering materials, take mild steel, okay, if you apply a load on that material, but if it changes the dimension, but whatever the deformation is very small. There is a fourth assumption. Next one, fifth assumption is the planes of members are not distorted. Distorted means change in shape. If you consider this is a rectangular cross section, if you apply a load on the body, once it is deformed, it remains only a rectangular shape only. It will not become a rhombus or any other shape, right? That is the fifth assumption. The planes of member not distorted. Distorted nothing but there is no change in shape of a body. Next, fifth one, the sections of interest are not very close to points of application of load. Now, if you apply a load here, if you pass an arbitrary cutting plane, I want to study what is the stresses induced on the throughout the length of the bar. Suppose I'm applying a load at this end. If you pass the arbitrary cutting here, there will be stresses are more. Yes, some initial, first or second class, some students, I think is asked the question. If I apply a load on the inclined load, right? So what will be that? What type of stresses are induced? If I apply a load here, there what happens? Their stresses are more. For theoretical analysis, will not consider a section at that point. Will consider away from the point, away from the loading point. That is the sixth assumption. The sections of interest are not very close to points of application of load. You are applying load here, but will not pass the arbitrary cutting plane here. We'll go for so far away from there, then go for arbitrary cutting plane. Then you'll see what will the stresses induced at that point, right? Then the seventh assumption is the member is completely free of stress when the load is removed. Means residual stresses are zero. What means if you apply a load, actually the third assumption is same. First also it is same here. If you apply a load only within the elastic limit only. If you remove the load, it comes back to original shape and size. If you not come back to original shape and size, there is a residual stresses are occurred here. Already inbuilt, the stresses are induced, right? That is what is the residual stresses. So you should, whatever the residual stresses are is, that should be considered as a zero. Right? These are the 7 important assumptions before going to study or derive the equation or study the stresses or deformation induced in a body, okay, by theoretical method. Is any doubt regarding these assumptions? The 7 assumption? Yes, Tejas is there. Tejas AV.
Yes, sir.
Any doubts regarding these assumptions?
No, sir.
Okay, thank you, ma'am.
Thank you.
Yeah, now the next slide is visible, Tejas.
No, sir. Yes, sir.
Deformation of bar.
Yes, sir.
Visible?
Yes, sir.
Yeah. Now, in the first module, what type of mechanical members you consider here? We'll consider the mechanical member is a bar, right? Bar is nothing but whatever the mechanical members are subject to only axial loads, those mechanical members will called as a bar. The axial loads, it may be a tensile or compressive nature. These are the examples already we given: steel rods, telescopic arms. In the human body, it's the arms, legs, etc. Now types of bars based on the cross section, how the cross section is varies along the length of the bar. The types of bars are classified. One is straight bar or uniform cross section bar. Now see that this case, this a body, this what is a rectangular cross section. Throughout this length, the cross section is same, right? Now this is called as a straight bar or uniform cross section bar. Throughout the line, the cross sectional area does not changes here. Now this is called as a straight bar or uniform cross section bar. Now this is another example for straight bar. Here, what is the cross sectional area is a circular cross section, right? Diameter you will get. Now the length, throughout the length, the diameter remains same. The cross sectional area remains same. Now this is a rectangular cross section. The width and thickness you will get. For circular cross section, the diameter will get. Throughout the length, the diameter will not change. Again, it is also a straight bar or uniform cross section bar, right? And next one is, second one is a tapered bar. Now throughout the length you can see this mechanical element. This is actually key, okay? And in your home also you can see this, the wooden ribs. When you want to mount the wall clock on the wall, first you may produce a hole, then you go for a wooden piece of this, insert it, then hammer it, then you go for insert the nail, right? Here you, what we see here, it is also throughout the length, the cross section is not same. What is a rectangular cross section? It is throughout the length, the cross section is not same. It is varying, uniformly varying. It is increasing. It is. Now this type of bar is called as a tapered bar. Of what type of cross section we are seeing here? Rectangular cross section. If it is circular cross section, is there? See that only this portion you can see that. If it is circular cross section is there, then it is called as a tapered bar of circular cross section. And another type of types of bar is a stepped bar. Now see that throughout the length, the cross section is not same here. Now here is one diameter, here is another. This is a tapered portion is there. Then here the decrease in diameter. Right, area decreases here. Here again area increases, decreases, area increases, again decreases. Throughout the length, the cross section is not same. For a period, over a length of the bar, the cross section is varies. Then called as a stepped bar. Yes, these are the different types of bar. And in slide also you can see that all the steel rods what we use in construction of buildings, those are comes under. Throughout the length, the cross section area is same. That is called the straight bar or uniform cross section bar. Now this you can see here, these are the drill bits. In the drill bit, the shank portion here, that is called as a throughout the length, the cross section area is not same. It is uniformly varying. That is called as a tapered bar. And one more you can see that here it is this third figure, second sketch. You can see the two different cross sectional area over the length of the bar. That is called as a stepped bar. These are the different types of bars. Yes, any doubt? Yes, Janvi is there? Janvi?
Yes. Yes, sir.
Yes. Any doubt, ma'am?
No, sir.
Yeah, okay, thank you, ma'am. Now you can see the next slide is visible.
No, sir. Yes, sir.
Yeah, deformation of uniform or straight bar. Visible, Janvi?
Yes, sir.
Okay, thank you, ma'am. Now, in the bar, when a bar is subjected to an external load, what is our intention in the mechanics of material? When external effect is there, that is equal to internal effect. The internal effect is one is internally distributed the forces, that is internal distributed forces over the cross-sectional area is called as a stress, and change in dimension is called as deformation. These two things you are going to determine throughout in our subject, right? Here the mechanical member is a bar. Under the first one is uniform bar or straight bar. Now consider, now how our aim is to, in this subject, our aim is to determine what is the deformation takes place and then what is the stresses induced in the bar. Now consider a straight bar. Okay, the continuous thick line shows the original component or initial body it is. Consider there's a continuous thick line. What we can see here on the screen, continuous thick line is that the bar it is the length of the bar you can represent as L. Consider a uniform bar of length is L and diameter you can see the side view. This is what we call as front view. If you go for left side view, see the left side view, you can see that is a circular cross section. Okay, that's why what we study in the engineering graphics, right? Front view, side view, top view, right? How the object is looks in solids. I think in solids you only studied about projections of, right? Projection of the solids. The same thing you are applied here. This is a front view of the bar. This is a side view of the bar, right side view it is. Now in the continuous thick line what we show here, the initial, the state of the bar it is. When it is subjected to an external force, what is the force here? We represent the force is P. When a bar is subjected to an external force P, what happens? Initially it resists to deformation, then internal stresses are induced here. Again, if you increase the load here, then what happened? You can see the dashed line shows a deformable body. Continuous thick line is original body or original bar. That once you apply a load P, what happens? The dashed line shows it's a deformed body. It's change in dimension, right? Now we are applying what load here? Tensile load. Once you apply tensile load on the bar, the length increases. What happens? Diameter decreases. You can see in the side view also, the diameter is decreasing here. In the front we can see the length is increases. How much length is increases here? Initial length, then plus change in length, L plus delta L. At the same time, in diameter, you can see the diameter is decreasing here. How much diameter is decreasing here? Initial diameter, then change in diameter. Here negative sign comes because negative sign means it is decreasing dimension. There is a negative sign comes here, D minus delta D. Now don't bother about the lateral dimension in the diametrical way, only concentrate only in the length direction. This is means nothing but is a one-dimensional component. Later we'll come to the change in dimension takes place in lateral deformation then. Okay. Then our aim is to determine deformation induced in the bar. Now before going to derivation, first we should clearly tell about what is this component is. Now consider a uniform bar of length L, the notation what we use, and diameter is D. Diameter is a D, subjected to a uniaxial load P, tensile load P. Then the deformation induced in the bar is delta L. Then how do you calculate delta L? First we are directly we go for apply Hooke's law. As you know that Hooke's law, stress is linearly proportional to strain. In order to remove the proportionality, we need a constant. That constant is E. Now you know that this is a one-dimensional stress strain relationship you call as. Stress is equal to Young's modulus into strain epsilon. Then as you know that what is the formula for stress? Stress is nothing but load by cross-sectional area. What is the load here? P. What is the cross-sectional area is? A. That is nothing but is a circular cross-sectional area. Pi by 4 d square. If you want, you can apply that also. Now here in general I take cross-sectional area is A. That is equal to Young's modulus as it is I kept here E. What is the deformation here? Change in length by original length, right? Now our ultimate aim is to determine deformation induced in the bar. This is change in length. Then change in length is equal to PL by AE. Now you should remember this is what is the rectangular box is there in the formula. Change in length in a uniform bar is equal to PL by AE. What is P? P is nothing but an external load is applied on the body. L is the length of the body and A is the cross-sectional area and E is the Young's modulus. What is the unit of deformation here? If you substitute all the units, the load is in Newton, length is in millimeter, cross-sectional area is in millimeter square, Young's modulus in Newton per millimeter square. If you go for apply the units and cancel, finally we will get deformation in millimeter. Now you should remember this formula. Change in length in a uniform bar or change in general, change in length of a bar is PL by AE. Now you can see this one here properties. What are the properties are there in this formula? There are three different properties are there. One is geometrical property. The geometrical properties are related to a geometry, the dimensions. What are the geometrical property of this? A bar means one is the length, second one is the diameter D or cross sectional area A. Or if you take a rectangular bar, the length is a geometrical property, width and thickness. Those are the geometrical properties. What is the loading property? Loading property means it is subject to an external applied force. Is a P, tensile load. Or sometimes instead of P, we use F also. The symbolically represented as load is F or P. That is the second property, loading property. Third one is material property. What is the material property here? Is a Young's modulus. That is important here. Material property is Young's modulus. Right? These are the three properties you should remember. Okay. Now, from the above equation, it is clear that for a given values of cross-sectional area, before going to this statement, just see that the deformation is directly proportional to applied load and directly proportional to the length of a member and inversely proportional to cross-sectional area and inversely proportional to Young's modulus. That is a material property, right? Now deformation is directly proportional to load, means if you increase the load, deformation also increases. Or if we increase the length of the body, the deformation also increases. What happens? The denominator term is there, there's the area and Young's modulus. If you decrease the area, if you increase the area, if you increase the area of the bar, what happens? The deformation is decreases. Is it right? It's inversely proportional here. Suppose if you increase the Young's modulus, material property of the Young's modulus of the material, if it increases here, what happens? Deformation also decreases. Now you should feel that the mathematical representation, what informations you'll get. The best way I can give here, the three statements you should remember. One is, if you write a word, it is having only one meaning or two meanings, etc. If you represent that one in terms of equation, it gives a 8 to 10 meanings. If you represent that the things are in the form of drawings that express 1,000, the 100 or 1,000 meanings that will give. Always you represent in the form of either equations or in the form of drawings. Okay, clear? Now remember this, delta L is equal to PL by AE. Now we'll go for see the statement here. From the above equation, it is clear that for given values of cross-sectional area A, length L of a body and the force P, means force is constant, L is constant, cross-sectional area is constant. Now what happens? Remaining one variable is E, Young's modulus. The deformation induced is inversely proportional to Young's modulus. Now see that equation here, deformation in a bar is inversely proportional to Young's modulus. That is, if the larger the Young's modulus in the material, it allows lesser the deformation. Okay, if Young's modulus of the material is more, means you go for take the same component. This component is made up of different material, means having different Young's modulus it is. If which one is high Young's modulus there, that material undergoes lesser deformation. That is the physical meaning. That is the best example what I have given, the plastic chair and metallic chair. If you take a plastic chair, one person, if you sit on the plastic chair, the chair can withstand that load. If you suppose 2, 3 or 4 members are sit on the plastic chair, means the plastic chair will not withstand that load, it will collapse. At the same time, the chair is made up of, take a metal, a mild steel. Now you can, one person can sit, 2 person can sit, 3, 4, 5 person if you sit on the chair, means the plastic chair will not deform or will not failure, because the Young's modulus of steel is greater than the Young's modulus of plastic. That is the importance of the deformation or the importance of material property. Yes. Any doubt regarding this derivation?
No,
If you
sir.
try to solve this derivation, then only you will get the one. Because when cluster comes to offline, then we'll derive it if possible. Otherwise, you should practice it. Okay. Is any doubt? Aradhana?
Yes, sir.
Oh. So now tell me the deformation formula, Aradhana.
For straight bar, sir.
Deformation of a bar, yeah.
PL by AE.
What is P?
Uh, load.
Yeah, load acting on a bar in Newton.
Bar.
Yes. L,
Length.
length of what?
Length of a bar.
Yeah, A, capital A,
Area of cross section.
area of cross section. Suppose if circular cross section is there, what is the area?
Pi r square.
Pi r square or pi by 4 d square. If it is rectangular cross section, the bar is in
Half.
rectangular cross section.
Half into base into height.
That is triangular. Triangular
Sir,
has a
2
rectangular section.
2 into L plus B.
Why it is 2? Rectangular cross section, width into
Sir,
height only. Right?
yes, sir.
Is
Yes,
a
sir.
rectangular cross section.
Yes, sir.
Next, last
Length.
parameter E. What is E?
Young's modulus.
Yeah, Young's modulus. What is the unit of Young's modulus?
Young's modulus. Newton per meter mm square.
Mm square, right. Now, from now onwards, all the geometrical property, the dimensions are expressed in millimeter only, not in meter. Okay?
Okay, sir.
Loading property is in Newton. Okay? So, Young's modulus is a material property. Yes. Thank you, ma'am. Yeah, next slide is visible.
Yes, sir.
Yes, sir.
Yeah,
Yes,
next slide
sir.
is
Yes,
visible.
Yes, sir.
Yes, sir.
The next slide is actually it is okay. I will make a correction here. Deformation of a tapered bar of bracket, tapered bar in that bracket, circular cross section. In this, in short term, instead of the cross section, instead of you writing whole cross section, in short form, you can write C bar S. Okay. Now the next one is deformation of a tapered bar. In the tapered bar, we have two types of cross section. One is a circular cross section throughout the length. What is the diameter? It is there, uniformly increasing diameter. I think it is visible, right? In the camera, you can see that. Yes, whatever I'm showing, the component is visible.
Yes,
Yes,
sir.
someone
sir.
give the response.
Yes, sir.
Yes,
So
sir.
not clear, sir. Not clear.
Yeah. Now.
Yes, sir.
Okay. Now this is only this portion you remember here. Now here, what is the cross section here? Circular cross section. Throughout this length, the increasing in diameter here. Okay, there is a
Yes, sir.
tapered bar of circular cross section. Okay. Another one is a rectangular cross section. This is a again tapered bar of rectangular cross section. What is the thickness is remains same. Okay. First we'll discuss the first point is a circular cross section. Now again here also now consider a tapered a bar of circular cross section of smaller diameter is what we represent as D1 and larger diameter is D2 and length of the bar is tapered bar is L. Yes. Now the
आम का क्लास चल रहा है चला उड़ा
yes,
इंसान
yes, any questions? Okay, so unmute yourself if you have a question, otherwise mute. Okay. Now consider a tapered bar of circular cross section of smaller diameter is D1 and the larger diameter is D2 of length is L. Now when it is subjected to an external force, a tensile force is P. If we view, this is a front view. If we view from the side view, you can see that the smaller diameter is a D1 and larger diameter of the tapered bar is D2. Right? Now, so if throughout the length, the cross-sectional area is not constant here, it's varying. If it is constant, is directly we can take deformation into the bar is PL by AE. But throughout the length, the cross-section is not constant, it is varying. For that, what I will do, we'll consider a small element, the elemental ring. You can see that in the side view is elemental ring. The small element of diameter is d suffix x. These are d suffix 1, d suffix 2, right? What is the diameter of the small element is d suffix x. At a distance of x from the d1, smaller end side here, at a distance of x from the smaller end, what is the thickness of the element is dx. Thickness of the element is dx. First we will go for what will be the deformation induced in the small element. Then we will go for integrate with the limit 0 to L. Then we will get the what is the deformation induced in the tapered bar. Clear? Now for that, see that statement, consider a circular tapering bar of length L and it is subjected to an axial force P. It is subjected to an axial force P. Let the big end and small end diameters be D2 and D1. The big end diameter of the tapered bar is D2 and small end it is D1. Now consider an element of diameter d suffix x and length is dx at a distance of x from the small end. At a distance of x from the small end. Now x is varies from what? 0 to L. Right? Now we know that in general formula, what is the deformation in the bar? It is in general formula deformation bar is delta L is equal to PL by AE. But here we consider a small element. What is the deformation in the element is delta L suffix x is equal to P into length of the element is L suffix x divided by area of the element is A suffix x and E. Now these are the two variables. The geometrical property is varying here. The loading is constant, metal property is constant. What is the geometrical properties? The dimension, length and cross-sectional area is changes here because it is we are consider only a small element. Throughout the length, the cross-sectional area is not constant. That's why these two are variable here. Now here, what is the length of the element? L suffix x is equal to, directly see the sketch here, it is dx only. Next, what is A suffix x? A cross-sectional area of the element is, we know that expressed in the form of a diameter is a pi by 4 d suffix x square. Again, d suffix x is known, it is unknown here. The diameter of the element is unknown. Then how do you determine the diameter of the how do you determine the diameter of the small element? Now the slide is visible. Yes, someone has to give the response.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Now, how do you determine the diameter of the small element? Now, you can represent the tapered bar again like this. Again, rewrite the diagram. Small end is D1, larger end is D2. The diameter of the element is d suffix x at a distance of x from the smaller end, and thickness of the element is dx. Right? Now, I want to determine what is the diameter of this small element. Now you can project the smaller end here up to the larger end. Now this is a D1, this is a D2. What is these two portions are there? It is a D2 minus D1. On the both side it is there, divided by 2. I think you know this, D2 minus D1 divided by 2. How do you get this one? Total it is a D2, right, minus D1. The remaining these two portions you will get here. Total it is D2 minus D1. On the two sides are there, right? That is why D2 minus D1 divided by 2 will get this portion. And this also D2 minus D1 by 2. But what is our aim? Our aim is to determine what is the diameter of the small element, d suffix x. How do you calculate d suffix x? Now from here to here and it is D1 plus y. Also this side also y plus y. Now you can see from the figure, what is d suffix x is equal to D1 plus y become 2 times of y, right? 2 times of y. Again y is unknown here, right? From this again y is unknown. How do you calculate y? we'll go for draw only this portion, the bottom below the axis. You consider this a triangle here. This is a triangle OAB, right? And at the elemental ring dx at a distance of x from the smaller end, that distance is called as a y. Now this is a what type of triangle it is? These are two triangles are there. One, this is a right angle triangle, this is also another right angle triangle. These two right angle triangles are having a same angles here. If you represent that, then it is called as a similar triangles. Right? The OAB and OCD are the similar triangles. Now we apply the similar triangle formulas here. From the similar triangle OAB and OCD, what is the, how do you get the ratio? The smaller side x divided by, for the larger triangle, what is the length here? L. X by L is equal to y by d2 minus d1 divided by 2. Now we will get this ratio. If you want one more ratio also, you will get OD by OB, right? So from the similar triangle, what is the ratio? We'll get OC by OA, that is equal to CD by AB, that ratio, that is equal to OD by OB. These are equations you will get from the similar triangle, right? Now here apply the concept similar triangle, that is x by L is equal to y by d2 minus d1 divided by 2. From this, which is the unknown here, which is our aim is to determine here in this equation, y is the unknown, right? You can, if you want, you can put the question mark over the y, that is the y is unknown. From this, y is equal to d2 minus d1 divided by 2 into x by L. Again, then substitute this y value into the equation 2. Substitute y value into the equation 2. Then in the equation 2, d suffix x is equal to diameter of the element is equal to d1 plus 2 times of what is the y value? Y value is d2 minus d1 divided by 2 into x by L. Substitute here. Now 2 get cancelled. Then if you simplify it, finally we will get d1 plus d2 minus d1 divided by L into x. Again, if you substitute this value into the equation number 1, again if further simplify it, each time we'll go for use this term d2 minus d1 by L. Now each time you are going to write means, again it's a each time you are going to write means is a lengthy and also it's time consuming. For that, what I will do, I will kept some constant here because these are numerator is in millimeter, denominator in millimeter. You will get cancel out. We will get a constant here. For that, I will put d2 minus d1 by L as a some constant. K is a constant here. Instead of representing d2 minus d1 by L, I will take it as K. Now, what is the diameter of the element here? D suffix s is equal to d1 plus K into x. Right? Now, this is the diameter of the element. But what I need? Cross-sectional area of the element is pi by 4. Substitute d suffix x is equal to d1 plus kx whole square. Now substitute that into equation number 1. Once you substitute that into equation number 1, yes, the slide is visible. The next slide is visible.
Yes, sir.
Yeah. Now
Yes,
once you
sir.
substitute that cross-sectional area into the equation number 1, what is the delta Lx? The deformation of the small element is p into the length of the element dx. What is the cross-sectional area here? Pi by 4 d1 plus kx whole square and metal properties E. Right? Now send this 4 to the numerator. Now this is the equation you get. 4 times of p into dx divided by pi into d1 plus kx whole square into E. Call it as is the equation number 3. Now this is the deformation of what? Deformation of a small element. But what is our aim? Our aim is to determine what is the deformation of the tapered bar throughout the length of the tapered bar. Then what we will do? We will go for integrate that equation. Integrate the equation 3 with respect to which limit here? What is the variable here? Length is the variable. X is varies from 0 to L. Now we will go for integrate the equation 3 with the limit 0 to L. On the left side, if you go for integrate here, for deformation for small element, integrate with 0 to L, we will get total deformation in the tapered bar, delta L. Then in the right side, integrate of this equation 3, 4 times of p into d divided by pi into d1 plus kx whole square into E. Now we will go for integrate the term with the limit 0 to L. Now in the integral term, take the constant outside. 4 is the constant. Whatever the load you are applying on the tapered bar is also constant. Pi is a constant. Metal property is also a constant. Take all those things outside the integral term. Now we will get integral of 0 to L 1 over by d1 plus kx whole square into dx. Now we don't have a definite integral for this. Now I'll send the denominator to the numerator. Now once you send the denominator to the numerator, what will become? It becomes a minus 2 d1 plus kx whole to the power of minus 2, the integral term. These are left side, it is constant here it is. Now you have an integration of, now it is in the form of what? See here in the right side, what is the line is there below, beside the line? Integral of ax to the power of n into dx is 1 over by a x to the power of n plus 1 divided by n plus 1. Now apply this integral rule. If you apply the integral rule, then you simplify it, and with the limit what? 0 to L. Now after simplification, then whatever you will get here, minus 1 get, then send the convert the numerator into denominator. This is 1 over by d1 plus kx with the limit 0 to L. Now first you apply the upper limit, then you apply the lower limit, then simplify, then finally we will get this value. There is a minus 4 into p divided by pi e terms of k, 1 over by d1 plus k into L minus 1 over by d1 will get. Again we put the k is equal to what? d2 minus d1 by L. Now substitute that k value. For further simplification, substitute the k value is d2 minus d1 by L. Now the slide is visible. Yes?
Yes, sir.
Yeah. Now substitute the k value is d2 minus d1 by L. Now substitute again, further simplify it. Okay. Now send this denominator L to the numerator. Now L get cancelled. Now d1 plus d2 minus d1, again plus d1 minus d1 get cancelled. Now whatever this, so I'll take only simplification here. That's why arrow mark is shown downward, or if you want, if you have a space, show upward also, then simplify it. Now it is in the 1 over by d2 minus 1 over by d1. Now take the LCM is d1 into d2. Now again numerator term will get d1 minus d2. Now d1 is smaller than the d2, right? For that take minus sign outside. Now d2 is greater than d1. d2 minus d1 will get. Now minus into, now you put this is as it is here. Now minus into minus plus you will get d2 minus d1, d2 minus d1 you will get cancel. Finally what you will get? 4 times of PL by pi into d1 into d2 into E. Or for a better understanding or better remembering purpose, what I will do here, I will make small rearranging the term here. Delta L is equal to PL by pi by 4 into d1 into d2 into E. Now this will be the deformation of a circular tapered bar. Now how do you remember this? In general formula, what is the deformation? PL by AE. In for uniform cross section area, what is area? It is pi by 4 d square. For tapered bar, for circular tapered bar, also you can see that delta L is equal to what? PL by AE you can take. What about A here? For tapered bar, area of the cross section you can take it as pi by 4 d1 into d2. You can easily remember that equation, right? That's why we rearrange the term here. PL by pi by 4 d1 into d2. Pi by 4 d1 d2 you can represent as area of the tapered bar into E. Now this is the deformation of a tapered bar of circular cross section. Right? Any doubt? Similarly, you tried this take assignment for rectangular cross section area, rectangular cross section tapered area. This is you can see the sketch here. At the smaller end, the width of this is a tapered rectangular tapered bar. At the smaller end, what is here? B1, smaller end, width or height you can say B1. At the larger end, it is B2. What is the thickness here? Thickness throughout the length is constant. Thickness will not vary here. Thickness is throughout the length is constant. And length of the tapered bar is there. It is subjected to what? A tensile force. Then you go for derive it, the same derivation. Only the integral term changes here. Then if you go for derive it, finally you get delta L is equal to PL by AE. A is nothing but here B2 minus B1 times of T into E, and one more term will get ln B2 by B1. So B2 is greater than B1. That's important here. B2 minus B1 you can take here, and also ln natural log of B2 by B1. Now take this is the assignment for the first in the subject mechanics of material. First assignment it is. Okay. Yes, any doubt?
Sir,
If you are confused here, you can search the textbook Strength of Material by Bobby Cutty or Mechanics of Material by K.V. Rao. Those two textbooks you can refer. If you refer the K.V. Rao, you can easily understand the theory part and also derivation, the importance of the subject. If you refer the Bobby Cutty, Strength of Material by Bobby Cutty, so many number of varieties of problem we can solve. Okay, now refer these two textbooks for our subject. Okay, after the syllabus I should tell that what are the textbook we should study that. These two textbooks we should study. One is Mechanics of Material by K.V. Rao. Another one is Strength of Material by Bobby Cutty. Okay, yes, any doubt regarding this derivation?
sir, have you sent this PDF, sir?
Sorry, yes. Okay, yeah, evening I'll send you Matt. Yesterday class and today's class also I'll send the video. Okay.
Yes, sir.
Okay, and at the same time notes also I will send in the group, WhatsApp group. After the class I will send it.
Okay, sir.
Okay. Okay. Any other doubt?
Sir, will you please send the code of that book, sir?
Sorry.
Code of that book, sir.
Core author.
Code. A code will be coming, sir, to get a soft copy.
Code that I don't know. In search in Google. Strength of Material by Bobby Cutty.
Spelling, sir, Bobby Cutty.
BHA.
Ah.
KATTI. Bobby Cutty. Strength of Material by Bobby Cutty.
Okay, sir.
I think you study in the elements of civil engineering. The same author is there, I think. Or in engineering mechanics. SS Bobby Cutty, I think. Okay, Bobby Cutty, yes, I think. Okay.
Okay.
Or K.V. Rao. One more is author is Mechanics of Material by K.V. Rao. Yes.
Yes, sir.
Shall I continue?
Okay, sir.
The last
sir.
one more derivation is there. That is deformation due to. So sorry for the interruption. Okay, next one is deformation due to self-weight. Now first one you consider deformation due to a straight bar throughout the length, cross-section area is same. Second one, deformation due to a tapered bar, if it is a circular cross-section or a rectangular cross-section. Now third one is that this is also a bar only, it may be a straight bar or tapered bar, but here consider straight bar due to what here? Self-weight. Now see the sketch here, is there any load is acting on this bar? Now see that, now this is the one component is placed, earlier what we consider, the bar is placed here, horizontal position, right? In the first and second derivation you can see the for straight bar, for tapered bar, the bar is in what position will kept here? What? Horizontal position. Now if the same bar is kept in vertical position, can you give the example for bar kept in vertical position in your home appliances? Have you seen the ceiling fan? Someone has to give the response.
Yes,
or else
sir.
I'll
Yes,
call
sir.
the name.
Sir, window rod also, sir.
Yeah, windows rod also, some are kept in, yeah, door rods. If you take a doors, if you close the doors and if you lock it, some doors what we use here, the bars are kept in vertical position, right?
Yes, sir.
Yeah, yeah. Now, suppose the bar, suppose you take best example ceiling fan, right? Or if you take what is one more is a lamp. What type of lamp here? Fluorescent, not LED lamps you take.
Sir, standing fan, table fan.
A table fan, okay, table fan also right. But if you take ceiling fan, best is the ceiling fan. Whatever the rod is there kept in vertical and whatever the rotor is attached and blades also attached, right? The whatever the rod is, the steel rod is there, that is separate to what type of load is self weight it is. Okay. So when the bar is located in vertical position, this end is fixed here. One end is fixed. Okay. Now here one more formula will come. When you kept a bar is in vertical position, see here, consider a bar in vertical position of length L and cross sectional area is A. It may be a circular cross section or rectangular cross section. Consider circular cross section, the area of the cross section is A. And one more term we use here, capital W. Capital W is nothing but what you call as specific weight. I think you studied this formula. Specific weight means weight per unit volume, right? What is the unit of specific weight? Newton per meter cube. You have a density, three types of densities are there. One is mass density, second one is weight density, and third one is relative density. I think you might be studied in the physics, right? Yes, Pradeep K.
Yes, sir.
You have studied these three densities, man. Mass density, weight density, relative density of a fluid. Say yes or no.
Yes, sir. Voice
Mass
is not
density is
correctly
nothing but
audible,
mass
sir.
per unit volume. Weight density is nothing but weight per unit volume. That
No.
weight density is also called as specific weight, right?
Hello.
Relative density means the density of a substance to the density of standard substance. Standard substance, what you consider as water. Okay. Now I will not go for in detail about that one. Here I concentrate only specific weight. When your object is kept in vertical position, whatever the entire weight of the body is acts vertically downward due to gravity. Right? Now specific weight will come. Weight per unit volume. From this weight is nothing but specific weight represented W. Weight we represent as also small w divided by volume is V. Instead of taking a W here, because two W's are there, one is capital W, another small w. Instead of that weight, I can represent as is a load P. What is the volume? Volume is nothing but area into length. Finally, what is our aim? What is the load acting on a bar when it's separated to an external, when it's separated to a vertical position? That is the load acting on the bar P is equal to specific weight into area into length. Remember this formula. Clear? Here there is no external load is acting here. Weight itself is acts vertically downward. How much it acts here? Due to the specific weight here, the load acting on the body is equal to specific weight of the body, the volume of the body. Volume is nothing but area into length. Remember this formula. Now we'll go for derive the deformation induced in the bar due to self weight. Before going to derive, the assumption, 7 assumptions should be applied. Then before going to derivation, we should represent what is the notation we use. Now consider a uniform bar of length L and cross sectional area is A, fixed in vertical position. Let the specific weight of material of the bar B is the W. Specific weight is the capital W in Newton per meter cube. Newton per meter cube. Weight per unit volume. Right? Consider an element again throughout this length. See that if you consider at this end, is there any weight is acting here? At this end, no. As the length increases, the weight is also increases because due to whatever that how much volume is contained here, the whole weight is acting at the CG, right? As the volume is increases, weight also increases here. For that, we will consider a small element here. Consider a small element of length. The length of the element is dx at a distance of x from the free end, right? The element is subjected to a load which is equal to weight of the portion BC. Now we'll consider a small element here of thickness dx. Below this portion, below that below the element is there, that mass, that weight is acting on that element. Now how do you calculate how much force acting on the element is? We know what is the volume of this element is area of this bar into length. Length of the portion BC is how much here? X. Now tell me what is the load acting on the element dx is, that is P suffix x is equal to the specific weight into area of the bar into what is the length of the bar, length of the portion BC is x. Now, first our aim is to determine deformation induced in the bar. We know the general formula for deformation induced in the bar is PL by AE. But here, we kept the bar is in vertical position. What is the deformation of the bar in due to self weight is, first you consider a small element. Deformation induced in the element is P suffix x, because load is varies as the volume changes here. As the length increases, volume also increases. P suffix x, the loading is a variable, load increases or load changes, variable it is. Length also is a variable. But whatever cross section, here it considers a uniform cross section bar, right? Area is constant, metal property is also constant. Where what is the load acting on the element is P suffix x. The general formula is specific weight into volume. But for an element you consider P suffix x is equal to specific weight into area into what is the length of the portion of the bar below this element here BC, that is x. W into A into x will come to the picture here. Now what is the length of the element is? Length of the element is d suffix, sorry, dx, not d suffix x, dx. Now substitute these two values into the above equation. Now P suffix x is nothing but W into Ax, length of the element is dx, area into E. Now area get cancelled. Finally you get W into x into dx by E. Now this is the deformation for a small element. But I need what is the total deformation in the bar. Then I will go for what? Integrate that element with the limit what? X, variable x from 0 to L. Now the total deformation in the bar is obtained by integrating equation 1 with the limit 0 to L. On the left side you go for integrate 0 to L, delta Lx, you get total deformation is delta L. On right side you go for integrate, W is a specific weight, is a constant. It's a what type of property? It's a physical property, right? E is also a constant, is a metal property. Take these two, W by E is take outside, we'll get only what? Integration of 0 to L, x into dx. Now integration of x to the power of n is nothing but x to the power of n plus 1 divided by n plus 1. Now it becomes x square by 2. Apply the limit 0 to L. First apply the upper limit, then you apply the lower limit, then you will get finally get WL square by 2E. W is W, capital W is here is what? Specific weight. Remember that. WL square by E. Without a load occurred on an external force occurred on a body, when the bar is kept in vertical position, the body will undergo deform it. How much it will deform here? It is deformation in the body is directly proportional to specific weight. As the way specific weight is more, is deformation is also more. As the length is also more, means deformation more. Again it is L square. It behaves as a quadratic equation. As the length increases, the deformation also increases. How it behaves? Not linearly. It is behaves non-linearly. And 2 is a constant, and it's a Young's bond is a material property. Now finally we will get the deformation in the bar when the bar is kept to vertical position, or deformation due to self weight is WL square by 2E. Remember this equation also. And one more note is there, instead of self weight, if you kept a bar in vertical position, instead of self weight, whatever the self weight is there, the same self weight we are going to apply an external force. The deformation in the bar subjected to a force equal to self weight. Suppose if you are kept in bar in horizontal position, whatever the self weight of the bar is there, then that self weight of the bar, that is you convert into a force, then you apply it. Now how much bar will deform here? As you know that deformation induced in the bar is delta L is equal to PL by AE. This is a general formula for deformation of a bar. Now P, what is the load acting on the bar is specific weight into volume of the bar, W into L. Now substitute this P value into the above equation. Now AA get cancelled. Finally you get WL square by E. That is also in millimeter. Now we'll go for compare equation 2 and 4. Equation 2 is deformation due to self weight. Second, equation 4 is deformation due to an external force is applied, that external force is equal to self weight of the body. Now when compare these two, which one will deform more? Whether it will deform, self weight will deform more, due to self weight the bar will deform more, or an external force is applied, that external force equal to self weight of the bar, that will deform more. Yes, Tejas?
Yes, sir.
Yeah, now tell me the compare these two equations, equation 2 and 4, which one will deform more?
2, 3, sir.
Equation 3 is the general formula. We are comparing only equation 2 and 4. See the equation 2 and 4, WL square by 2E is there in equation 2. In equation 4, WL square by E is there. Which one will deform more?
2, sir.
Equation 2 deform more. Wrong. Yashwant D. Raj. Yashwant D. Raj. Is not there. Yogesh. Okay, now see the below this here, below the statement itself. From equation 2 and 4 shows the deformation in a uniform bar due to self weight is half of the deformation due to force equal to the self weight. Means an external force applied on the body due to whatever the force applied, that is equal to self weight, means that deform more as compared to deformation due to self weight. That is the statement here. Now remember these two equations. Right? Yes, the summary of this class today we discussed about, so the overview of the previous classes, what we discussed. Then we'll consider the assumptions are very important. 7 assumptions. The material is obeys the Hooke's law. The material is homogeneous and isotropy. The member is loaded within the elastic limit. Deformation is small. We consider the plane remains same plane, not distorted. Now whatever the section of interest we consider is far away from the applied load and there is no residual stresses. Next we discussed about the mechanical members are subject to only an axial loads. Those we call as a bars and types of bars. Then when bar is subject to an external load, our ultimate aim is to determine one is stresses, another one is deformation. Here stress is remains, what is the formula for used for stress is load by cross sectional area, that will not change. Only deformation will change based on the type of bars here, the straight bar, a tapered bar or stepped bar. Okay, stepped bar we'll discuss in detail in later. In next class we'll discuss. These are the derivation you should remember and should practice once or twice. Practice for exam point of view. Which one is very important derivation is, this is a very important derivation, deformation of a tapered bar, or it may be a circular cross section or tapered cross section. So maximum 90 to 95% circular cross sections will come. We'll see in that question paper, previous year question paper, come to know that derive and deformation of a tapered bar, circular tapered a bar. These things you should write. Okay, for exam point of view, you should practice this derivation and also remember the formula for if you want to solve that problem based on that type of bars. Okay, yeah, next class we'll discuss these things. Okay, any doubt? Any doubts?
No, sir.
No doubt. I think when offline classes there, it's easy to understand the derivation because some constraints are there in that. Because if you have a tablet, then we go for derive that equation. But here for slides purpose, it's not good for the derivation. Theory you can easily tell, but for problems or derivation, it's difficult to understand also, right? Yes. Yes, any other doubts? If you have doubts, now you can ask. You unmute yourself, then ask yours. Ask the doubt. Yes. One ನಿಮಿಷ ಸರ್ ರೆಕಾರ್ಡ್ ಆಗ್ತದೆ. Yes? No doubts? Shall I wind the class? Wind up the class? Yes, no one has given the answer.
Okay, sir.
Yes, sir.
Yes.
Yes, sir.
Okay, ma. Okay, thank you for attending the class. Okay, I'll send the notes. Okay, and also video. So tomorrow and day after tomorrow you have holidays, right? Just go through it. If you have doubt, then I think in Wednesday we have class, right? In Wednesday we'll discuss. Okay, thank you guys. Thank you for listening my class. Thank you one and all.
Thank you, sir. Thank you,
Okay,
sir.
I will end up my